Hello, everybody. Before we begin, I will welcome you to our webinar presentation on Capture, Condition, and Confidence, Raising the Standard of Municipal Asset Data. I would like to thank you and the people at Municipal World for the opportunity to put on this presentation for you today. And as this is an exciting technological field that is rapidly changing and steadily improving, but already bringing unprecedented value to municipalities, big and small, across Canada, the United States, Mexico, and the world. My name is Alex Silstowski, and I'm the Development and Regulation Manager at Eagle Engineering and Consulting. I've been in the Earth measurement or geomatics industry since 2014, earning a diploma in geomatics engineering from the Centre of Geographic Sciences in Nova Scotia, Canada, and then an engineering degree from the University of New Brunswick in New Brunswick, Canada, in geodesy and geomatics engineering. I'm also a reality capture evangelist, participating in advisory and community organizations across Canada and the United States, including the Reality Capture Network, the United States Institute on Building Documentation, the Committee XYZ, and I've founded my own organization called the Can Slam Circuit, where manufacturers, academia, and industry get together to evaluate these technologies, like the ones I'm about to show you today. Uh, in order to better inform and serve customers like you and to promote responsible use of these technologies so that we can support their development or adaptation. The company I work with, Eagle Engineering Consulting, is based out of Fredericton, New Brunswick, Canada, and was established in 1989 as a telecommunications design company. Our president, though, Dan McCarthy, believes in technological innovation and began using the technology I'm going to show you here today to speed up information collection for infrastructure assessment, documentation, and permitting. Eventually, the accuracies and area coverage of adopted technology pushed Eagle outside of telecommunication as municipalities and energy companies started taking notice of what we're doing. As a result of this attention, Eagle's surface offerings began to evolve greatly. But we're here to talk about you and your operations. So, municipal teams are often responsible for managing massive areas with little time and limited resources. Yet, we spend time sending multiple crews out to the same places multiple times a year to get information. Why? Because sending them out once to collect absolutely everything is costly, lengthy, and almost guaranteed to be just too much. Infrastructure information can become inconsistent between both projects and departments. Documentation systems and standards can differ even in the same municipality. Engineering standards are different from mapping standards. Departments like accounting don't necessarily care where an asset is as much as the emergency or engineering departments would. Quantities matter to those who control the assets, location matters to those who interact with them, and all this information depends on a person's ability to collect and report accurately. There's a lot of information that needs to be collected from any one location. And so many workflows still rely on manual collection, manual review, outdated records, and repeated site visits to gather missing details and get a better picture of what's out there. And finally, accessing current information quickly and consistently can be a challenge for engineering, planning, and asset management teams, just in general. And yet, despite all of that, municipalities today are under increasing pressure to maintain aging infrastructure while balancing those limited budgets, that limited staff, and growing their service expectations in growing communities. At the same time, teams are being asked to make more informed and defensible infrastructure decisions using data that's often incomplete, outdated, or difficult to access consistently. Whether it's roads, sidewalks, bridges, or utilities, having reliable visibility into asset condition is becoming increasingly important for planning, prioritization, and long term asset management. A big part of that challenge is making sure infrastructure decisions are supported by accurate and accessible information. Many municipalities are still relying on infrastructure information that has been collected over long periods of time across different projects, different departments, different consultants, and different systems. As a result, records can become incomplete, inconsistent, lost, difficult to maintain, or disconnected from current conditions in the field. In many cases, information is collected for a specific project, used once, and then becomes difficult to access or reuse later. That creates challenges for engineering review, asset management, planning, and long term infrastructure decision making. One of the biggest opportunities today is creating infrastructure records that are easier to update, share, and reuse across the organization that are harmonized with each other. And that naturally brings us to the traditional methods of doing this kind of data collection. So, traditional infrastructure data collection methods have supported municipalities for years, but many of those workflows can become difficult to scale as infrastructure networks grow and service expectations increase. A lot of condition assessments and documentation work still depends heavily on manual field review and human interpretation, which can make data collection time consuming and inconsistent between projects or teams. Coverage can also be limited because collecting detailed information across large roadway or infrastructure networks often requires significant field time and repeated mobilizations. There are also safety considerations, whether crews are working near traffic, active roadways, or difficult environments. Coordination can become troublesome as crews are rotated or take time off, and regional nuance or unique areas and objects can add further confusion and time. Some reasons why municipalities are exploring newer collection technologies are to improve consistency, efficiency, coverage, and long term usability of the infrastructure data. So, as you might imagine, with the evolution of the technology and the history, municipalities are beginning to shift away from collecting infrastructure data only for individual projects and towards creating reusable digital infrastructure records. The focus is becoming less about isolated inspections and more about building complete, accessible data sets that can support planning, engineering, GIS, asset management, and future projects over time. There's also growing interest in workflows that improve safety, reduce repeat site visits, and provide better accessibility and visibility across large infrastructure networks. A major change happening today is that infrastructure data is becoming something organizations expect to share and reuse across departments instead of recreating from scratch every time a new project starts. That shift is what's driving increased interest in technologies like LiDAR and reality capture. And so that brings me to my buzzword, reality capture. It really is an umbrella term for technologies that collect accurate digital information about real world infrastructure and environments. There isn't just one way to do it. Different collection methods are used depending on the project, environment, and level of detail that are required. That can include vehicle-based mobile mapping for large roadway networks, drones for aerial collection, static or stay still LiDAR scanning for detailed infrastructure documentation, and portable systems for sidewalks, interiors, or hard to access areas. The common goal across all of these workflows is creating accurate, reusable digital infrastructure records that can support engineering, GIS, planning, asset management, and those future projects. The next step is understanding one of those core technologies behind many of these workflows, and that would be LiDAR. At a high level, LiDAR works by sending out millions of laser pulses and measuring how long they take to bounce back after hitting surfaces like pavement, curbs, signs, bridges, and other infrastructure features. Each return creates a precise 3D point in space. When millions of those points are combined together, they create a detailed digital representation of the roadway and the surrounding environments. For municipalities, the value is not just the visualization, it's the ability to create accurate, repeatable infrastructure records that can support engineering review, condition assessments, GIS integration, asset management, and long term planning from a single collection workflow. And those millions of measurements per second create what we call a point cloud. A point cloud is the digital data set created from the LiDAR itself. Each individual point represents a precise location in 3D space. And when millions of them are combined together, they create a highly detailed representation of the real world infrastructure and environments. Fun fact though, what you're seeing in front of you, that those are not a forest and trees, that is not a roadway. Those are the measurement points that your brain is interpreting as things. The computer doesn't necessarily see them the same way that you do. These data sets, though, can also be used to create interactive 3D models that allow teams to visualize, review, and analyze infrastructure conditions remotely and more precisely. Because the data is measurable and GPS coordinated, teams can use it to extract distances, elevations, slopes, clearances, offsets, asset locations, and other engineering information directly from the data set. One of the major advantages for municipalities is that information can often be reviewed later without needing repeated site visits, helping reduce field mobilization while improving consistency and long-term usability of those infrastructure records. What makes these workflows valuable is not just the way the data is collected, but what municipalities can do with the information afterwards. Better infrastructure visibility can support more informed planning, more consistent condition assessments, and faster access to infrastructure information across departments and projects. It can also reduce the need for repeat site visits and create more complete records that remain useful long after the original project is complete. Ultimately, better infrastructure data helps support more confident and defensible infrastructure decisions. To best illustrate this, we figured that we'd walk you through some of the practical municipal use cases and examples of how these technologies are being used to support infrastructure planning, documentation, and asset management. One of the biggest advantages is the ability to create objective and repeatable infrastructure records that can support engineering review, condition assessments, GIS integration, and long-term asset management. Excuse me. These workflows can also improve safety and efficiency by reducing repeated site visits and minimizing the amount of time crews need to spend working in active roadways or in difficult field environments. Another major shift is that the same data sets can often support multiple teams and future projects instead of being collected once and archived away after a single use. Ultimately, the value is not just in collecting the data, it's in creating reusable infrastructure records that can support better long-term planning and decision making across the organization. A prime example of how a single collection workflow can support multiple municipal needs at the same time is corridor infrastructure capture. Instead of collecting data separately for roads, sidewalks, signage, utilities, and asset inventories, a corridor capture can create a shared infrastructure data set that supports many different departments and future projects. These data sets can be used for roadway and pavement review, corridor measurements, asset locations, utility documentation, signage reporting, engineering review, and long-term capital planning. One of the biggest advantages is that municipalities are creating infrastructure records that remain useful long after the original collection is complete. Being able to compare that historical information against newly acquired information more directly. And rather than collecting data for a single purpose, the information can continue supporting planning, maintenance, GIS integration, and future engineering workflows over time. Road and pavement condition assessments are one of the areas where reality capture workflows are seeing growing adaptation within municipalities. Using mobile LiDAR and imaging systems, municipalities can collect detailed roadway information at corridor scale while creating datasets that support PCI-based pavement review, crack identification, surface condition analysis, and other engineering evaluations. Because the collection is repeatable and GPS coordinated, teams can also compare conditions over time and create more consistent infrastructure records across different projects. Bridges and structure documentation is another area where reality capture workflows can provide significant value for municipalities and engineering teams. LiDAR and scanning technologies can be used to capture highly detailed bridge geometry, deck conditions, structural clearance, and surrounding infrastructure environments. These datasets support engineering review, 3D modeling, digital twin development, and long-term infrastructure documentation while creating measurable and repeatable records for existing conditions. Because the data is GPS coordinated and reusable, municipalities can also perform year over year condition monitoring and compare infrastructure changes over time without relying solely on traditional manual documentation workflows. The result is a more complete and defensible infrastructure record that can support inspections, planning, rehabilitation projects, and long-term asset management. Asset and right-of-way mapping is another strong application for reality capture workflows because a single corridor collection, again, can support multiple inventories, measurements, and planning needs all at the same time. LiDAR and imaging systems, using these, municipalities can extract roadway assets such as poles, signage, utilities, barriers, sidewalks, and other linear infrastructure directly from the data sets. These workflows also support right-of-way documentation, corridor measurement, offset analysis, and georeference infrastructure mapping without relying entirely on manual field collection. Because the information is GPS coordinated and measurable, I've already mentioned this before, but it's easier to integrate this information into GIS and for asset management systems while supporting those future engineering projects. One of the biggest advantages is that municipalities are creating reusable corridor records that can continue supporting the infrastructure after the initial collection. These are a few examples of how reality capture workflows can support more specialized infrastructure monitoring and assessment applications beyond traditional mapping and inventory collection. For example, on the left, data sets can be used for encroachment monitoring by comparing corridor conditions over time or in an instant and identifying the changes or objects that may impact that right of way. So what you see there is all of the objects that were detected within a sidewalk area. Some of them might be people, some of them might be pets, but most of what you're seeing there is actually the returns from the vegetation that has grown into the right of way for the pedestrians as they walk down the road. But we can also support structural monitoring and interior documentation workflows where precise measurement and repeatable conditions are essential for facility management or infrastructure review. And on the right, the retaining wall example shows how detailed data sets can support condition assessments, geometry review, and targeted engineering analysis without relying entirely on manual field measurements. One of the key advantages is that these workflows can create measurable and repeatable infrastructure records that teams can revisit later in full context for additional analysis, comparison, and future project needs. And further examples on the left, you'll see a guardrail survey example where LiDAR and imaging data can support infrastructure inventories, offset measurements, condition review, and corridor safety assessments. This is done through either automatic or semi-automatic means, meaning that we actually have means to get the computer to do these most of these measurements for us, which greatly increases our productivity time. In the center example, the overpass had actually been struck twice in the same week by oversized vehicles. And a few months earlier, the structure had already been scanned as part of one of our corridor documentation workflows. And because of that, there was a data set that already existed, and the team was able to quickly revisit the digital record after the incident to review measurements, clearances, existing conditions, all without starting from scratch. That's a good example of the long-term value of reusable infrastructure data sets. The information collected for one purpose can then be later used to support other investigations, other engineering reviews, and future planning needs when unexpected events occur. So On the right is a vegetation class detection example. So where municipalities and utilities can identify vegetation encroachment over overhead infrastructure and transportation corridors using measurable spatial data. Same thing as the sidewalks, but instead of using the sidewalks as a reference, we use the cables or the suspended infrastructure as the reference for the computer. This shape, tell me everything that's within X distance of this shape. These types of workflows help municipalities move from reactive field review towards a more proactive infrastructure monitoring, planning, and risk management. Tree inventory and mapping is another really good example of a very efficient application of mobile mapping and reality capture. We use it to identify vegetation locations, heights, clearances, and potential conflicts near infrastructure corridors. In the center of this particular slide is a manhole or underground structure that was scanned where detailed 3D data sets can support confined space documentation. So basically, one of these holes can be drained, and then instead of sending a person in who may end up not collecting all the information, we send a scanner down there instead to not only deny persons from unsafe working environments, confined space entry, but to fully document that internal space to the satisfaction of a survey, review, or engineering design. Uh, this allows for the infrastructure to be reviewed and the long-term asset record to be established without relying on manual sketches or photographs. And then finally, on the right is a floor flatness analysis where, I live in Canada, hockey's pretty important here. Uh, high accuracy scanning can support construction verification, facility documentation, and quality control workflows for large indoor environments. So that one in particular, we were doing a floor flatness survey in order to aid in the construction of a refurbished rink. But I could go on and on and on. On the left of your screen now is a volumetric assessment. So this is where LiDAR data sets are used to calculate stockpile volumes, earthwork quantities, including cuts and fills, and material movement using measurable 3D data instead of manual estimation tools. In the center is an existing condition documentation example. So before construction begins, detailed scans can capture the exact condition of a site, roadway, or structure. So teams have defensible records on pre-construction conditions for engineering review, coordination, and future reference. And then finally, on the right is a construction progress monitoring example where repeat scans can document how a project changes over time, where it might differ from the original designs, and help teams compare progress against the schedule and the previous site conditions. These types of workflows can help create more accurate and repeatable project records while improving visibility throughout planning, construction, and long-term infrastructure management. And while you may feel like I've thrown a lot of information at you today, I feel like I have given you nothing. This is a very robust industry with varying degrees of accuracy that can meet your needs today. And unfortunately, I just have too many things to talk about in order to cover it all. So the goal of this session was really to provide a practical introduction to how municipalities are beginning to use LiDAR and reality capture workflows to support infrastructure planning. Uh, and what we covered today is only a small example of the types of workflows that are possible. Every municipality has different infrastructure challenges, different data sets, and different operational priorities. That's why we also offer more focused learning sessions tailored to specific teams, specific departments, and general municipal workflows. These sessions can go deeper into areas like pavement assessments, corridor mapping, GIS integration, asset inventories, bridge documentation, construction monitoring, digital twins, and like a plethora of other infrastructure applications relevant to you and your organization. So, if your team is interested in exploring potential use cases or learning more about how these workflows can support your infrastructure programs, we encourage you to please feel free to reach out to us using the contact information on the screen. So, once again, my name is Alex Silstowski. I would like to thank you for taking the time to listen to this presentation today. And of course, we'd be happy to answer any questions.